Hello friends, welcome to engineering tutorial. So in today's video we are going to resume our discussion on power systems engineering. So it's been a while since I have uploaded any video on this topic. So we will resume our discussion. So before that I want you to watch the introductory videos related to this subject in the power systems engineering playlist. So today's topic of discussion, it will be a long one. It will be a series of videos. So it is parameters of a power transmission line. Okay. So before going deep into this topic, we will be discussing a series of basic introductory concepts which will be related to network theory or circuit theory, just to give you a quick idea of what we are going to cover in the parameters of power transmission line. Okay, so mainly when we consider a power transmission line, the important parameters, important components of a power transmission line, it is three: resistance, inductance and capacitance. Okay, and their combinations. So these three things, they contribute to the different effects, whatever impact is caused by on a power transmission line, it is because of these three parameters. So in the next series of videos will be in a quick way we'll be covering each concept: resistance, inductance, capacitance, the various related concepts from the point of view of power systems engineering. Only those things we'll discuss which will have a role to play in our discussion related to parameters of a power transmission line. Okay, so we'll be starting with the first important parameter of a power transmission line, which is resistance. Okay, so the basic concepts related to resistance and resistive circuits, that we'll be discussing. So starting with the very basic concept, in a quick manner we'll be discussing and not be going into the detailed nitty-gritty of it, just to give you a brief idea about these basic concepts, so that when we discuss the parameters of transmission line, power transmission line in a detailed manner, you will not have any confusion. A quick revision. So resistance and Ohm's law. So the resistance of a conductor is the property because of which it opposes the flow of charges, the flow of electrons, the flow of current through it, because current flows because of the movement of charges, the movement of electrons. So Ohm's law states that the current flowing through a conductor is directly proportional to the potential difference applied across its two ends. And here the important condition is that temperature and other physical conditions such as dimension, changes in dimension, they are all constant, they do not vary. So current is directly proportional to potential difference. So it can be mathematically expressed as V is directly proportional to I, or I is directly proportional to V. Same thing, V is equal to IR, where R is resistance, I is current and V is the potential difference or voltage, and V by I is equal to R. Okay, the ratio of voltage and current, voltage divided by current. So this graph of an ohmic conductor, it is a straight line passing through the origin, and the slope of this line, that gives us the resistance. Okay, so here the factors which affect resistance here, that is length, cross sectional area and nature of the material. So it has been experimentally found that the resistance is directly proportional to the length, inversely proportional to the cross-sectional area, and there is another parameter which is called as resistivity or specific resistance, which arises because of the nature of the material. So combining these all factors, we get resistance is equal to rho L by A, where L is the length, A is the cross-sectional area, and rho is the resistivity of the material. Okay, this is the change or the resistance, how it depends upon the dimensions of the material, size, shape, all that. Then another important concept is current density. So current density, simply at any point inside a conductor carrying current, the current density is expressed as current per unit cross-sectional area. Okay, so we consider an imaginary area which is held perpendicular to the direction of flow of current at that point, and the current by area, the ratio of the current flowing to the cross-sectional area, that gives us the current density. The unit of current density is ampere per meter square. So here the unit of resistance, I think we have covered, the unit of resistance is ohm, and here the unit of resistivity or specific resistance is ohm meter. Okay, I'm assuming that you have a good idea about this, but just to get a quick revision, I'm doing this. So current density, if we consider an imaginary area here, okay, let's say we pick an imaginary cross-sectional area here, and current is flowing like this. So current density will be current divided by the imaginary cross-sectional area, which is held perpendicular to the direction of flow of current, and the unit will be ampere per meter square. Okay, and then we have conductance. So conductance simply is the reciprocal of resistance. So it is the opposite of resistance, that is the ease with which electric current or charges or electron flow through a material or a substance. So it is the reciprocal of resistance. It is represented as G. G is equal to 1 by R. And in terms of the dimensions, length, cross-sectional area, and resistivity, it is expressed as G is equal to A by rho L, simply the reciprocal of the expression of resistance, rho L by A. So here 1 by rho is sigma, which is the conductivity of the material. So it can also be expressed as G is equal to sigma A by L. Okay. So now we will be discussing about another important thing which will come into play in our discussion related to power transmission line, resistance of power transmission line, which is the temperature dependence of resistivity and in turn resistance, because we know that resistance of a conductor is given by R is equal to rho L by A, where rho is resistivity or specific resistance, L is length, and A is cross-sectional area. So here how this rho or resistivity, it fluctuates or it varies as per the temperature, the surrounding temperature T. So the resistivity rho of a conductor, it is dependent on the temperature T specific at particular point temperature T, as rho is equal to rho 0 into 1 plus alpha T minus T0. Here T0 is the reference temperature, any particular temperature with respect to which we want to measure or study how the resistivity changes at any higher or lower temperature T, specific temperature T. So T0 is the reference temperature, okay, the reference. Normally it can be taken as 0 degrees Celsius or 273 Kelvin. So it varies, it depends. So T0 is the reference temperature, and rho 0 subscript O, that is the resistivity at the lower reference temperature T0. Okay, the resistivity at the reference temperature T0, that is the reference resistivity value. And rho is the resistivity at particular temperature T, capital T, this. And alpha is the temperature coefficient of resistivity, which is expressed as this. Alpha is equal to rho minus rho 0 by rho 0 into T minus T0. Okay, so this is the variation of resistivity with respect to temperature. Then temperature dependence of resistance, because resistivity will impact resistance too as per the relationship rho L by A. So here the resistance RT of a conductor at a particular temperature T is given as RT is equal to R0 into 1 plus alpha into T minus T0. Again, T0 is the reference temperature, R0 is the reference resistance, that is the resistance at the reference temperature, lower reference temperature, and R subscript T is the resistance at particular temperature capital T, and alpha is again the temperature coefficient of resistance or resistivity. That